So section 5.3 is about finding the shortest route, okay? So 5.3 gives you this idea of saying, okay, what happens if instead of trying to find the shortest way to go from a starting point to hit all the vertices and come back to the starting point, which is what the traveling salesperson did, right? That was a Hamiltonian circuit, and we were trying to come back to where it began. What if we just want to find the shortest distance between point A and point B? So we give us like multiple starting points. Like think Google Maps for a moment, right? Let's say you put in your location, the Google Maps picks up on your location, says, okay, I get the fact that you're right here. Now, what happens if you then put in a second point and say, okay, I want to go to school today? Do y'all all agree that there's multiple different routes you can take to go from your house to school? And the whole point in having something like Google Maps or GPS pulled up is that it's going to find the shortest route possible to get you from point A to point B and even reroute you in the middle of it, right? Does that make sense? Yes. Okay. So this shortest route algorithm is not trying to find the shortest distance from start back to start. It's trying to say, what's the shortest route I can take from the start point to any other vertex on the problem? Okay? So that's what this thing does. Your algorithm says, okay, great, start with a starting vertex S and circle it. So in this problem, let's label A as S. Okay, so we're going to come over here, we're going to circle vertex A, and we're going to rename it S. Easy enough so far. If the problem says start here, you just circle it and rename it S. Then it says, okay, great. I want to look at all the edges that have S as an endpoint. So here's what we're going to do real quick. We're going to look for all the different edges that have S as an endpoint. So we can list SB, and SC. Make sense? So we have a total distance. SB is 5, SC is 2. Which one's the shortest? SC. So we're going to go ahead and kind of circle that one for a moment so we can know that that's the one we chose to do. We're going to darken the edge from S to C, and we're going to circle vertex C. Easy enough? Now, it says, examine anything uncircled that's adjacent to a circled vertex. There's a couple different routes we can go now, right? The catch is, it's got to be directly adjacent to a circled vertex. So the first one we have, isn't SB still adjacent to one of our circled vertices? So we're going to start a new list. We're going to list SB, and we know that takes a total distance of 5. We could list SCB for a total distance of what? 4. We could do SCD with a total distance of 6, or SCE with a total distance of 8. Which of those is the shortest? SCB. So we go from S to C and then highlight down to B, circle B. Okay, that's done. Now we do it again. Do you see how SB is no longer an option because B is already highlighted? So if you want to come up here and mark through that one saying that's no longer an option, but don't we still have SCD and SCE as options? Make sense? So we can rewrite those. So we can list SCD with 6, SCE with 8, and now we can add in SCBD with a total distance of 7. It's from any circle that we can step off, but we have to be adjacent to the circle. Okay? So now from here, the shortest one's going to be SCD. So we find SC and then highlight down to D. And we keep going. Well, now because we've already gotten to D, we're not going to do this SCBD option, cross that one out. bring the SCE down with 8, and then I could go SCDF, right? So SCD is 6 plus 4 is 10, or I could do SCDE, which is 6 plus 5, 11. We pick the short of the two, highlight SCE, circle E, and now we only have 2 options, right? Our last 2 options are going to be, since we've already used E, this one's out, so SCDF, which is still 10, or I could do SCEF, which is going to be 8 plus 3 is 11. You pick your shortest one and highlight from D to F. And what you'll look at here is this concept isn't trying to say go start back to start. It's simply saying if I wanted to start at S and then get to say vertex E, the shortest route to get from S to E is to go SCE for a total distance of 8. If I want to go from S to F, the shortest route is to go SCDF, and it picks that one. So recognize the fact that you're getting a lot of different options now, and they're all going to sound really similar, and it's up to you to figure out which one we're looking for. Are we trying to do a traveling salesperson problem where we're starting, going to every vertex exactly once and back to where it began? Or are we trying to start at some point and find the shortest distance from that start point to every other point? Yes, sir? Yes and no. What we've been doing is we've been going and coming back to where we began. Right. But that's just it. Now you not only have the shortest distance from S to F, you have the shortest distance from S to every single vertex up there. So this is more like what Google Maps does. It says, okay, great, give me a start point, give me an end point, and I'm going to give you all the different options you can take from start to finish. And generally what it's going to do, it's going to give you some options. It's going to say, okay, here's the deal. This is the shortest one by distance. This is the shortest one by time. And here's another alternative in case you don't want to use a highway. Does that make sense? So it gives you a lot of options in there. Only catch is, whereas we have to go through and do each step individually like this, it takes us a while to get through it all, because Google's using these big computers to do all the processing for them, it makes it seem really quick. So this is the example that's going to get you into really, really understanding how Google Maps is working. Okay? So take some time, look over the problems. Let me know if you need another example.